All right, hello, class, and welcome to our first ever digital lecture. It's weird. It's weird. Welcome to the show. I was doing some test runs earlier this morning, so everything was all good there, but I'm waiting to see what the time delay is looking like. Yeah, hi Ryan. This is going to be interesting. You know, what's going to be interesting too is how interesting how I manage typing and talking. Sorry, I'm just checking on the feed. Let's see. Oh, looks like I'm live now. Okay, cool. Well, all right. So we're gonna go ahead and get started. Our song of the day is maybe a little bit of wishful thinking. We'll see. Our song of the day is... Whoa. That's a little sloppy. There we go. Oh, that's still a little sloppy. Hang on. There we go. Our song of the day is, again, a little bit of wishful thinking on my part. It's Smooth Sailing by Queens of the Stone Age. And I will be linking that in the video after the stream. The video will be available for watching later. Yeah. Song of the day. Smooth Sailing. We'll see. Yeah, totally weird. Okay, volume's fine. Is it quiet for anyone else? All right, it looks like... Oh. Okay, sorry. I'm going to silence my cell phone. All right, so welcome to our first online lecture. It only took us 2 minutes and 32 seconds to get here. I'll be, like I said earlier, keeping the Red 5 standing by. Awesome. I'll be gold leader, which makes me Jack Porkins, and I get incinerated a little later in the attack on the Death Star. So, let's go ahead and start talking about some chemistry. Oh, hang on. That was far too jarring. I need to alter my... Okay, hang on. I'm getting some... Windows is setting to be a really fun thing at the moment. But let's see if I can get my window back. There we go. Okay. Boop. There we go. Okay. Sorry, off to a bit of a choppy start, but doing the best we can. Okay, I'm going to be keeping an eye on your comments. So if you have questions as I go through, and I'm not seeing them, I apologize. I'm going to do my best to multitask, but this is a new experience for me as well. Doing this with multiple people. I've done this one-on-one, but the group thing is new. So we are, as our home slide tells us, in the middle of a discussion on thermochemistry, and getting back to kind of giving us all a refresher of what we've covered. We have learned that there are two, when we talk about thermochemistry, when we talk about transferring energy, we're talking about moving energy back and forth between the system, right, which is whatever we're looking at, and the surroundings, all right? Those are the two kind of entities that we transfer heat to and from. And there are two different ways, as we've talked about, to transfer energy back and forth. One is through thermal energy transfer, which we have the equation Q equals MCAT. All right, and then the second way that we can transfer energy is through work, and we know that that expression is work is equal to -1 times a constant pressure times our change in volume. And this gives us our expression, the change in energy, change in energy is equal to thermal energy transfer plus energy transferred through work. Now, something that I want to zero in on for a minute is work. Now, because work is dependent on a change in volume, most chemical reactions that we run are not accompanied by a change in volume. All right, there are gas phase reactions, but when you walk into lab, for example, and you set up an acid-base reaction, you're mixing two liquids, your volume is constant throughout the expression. And when volume is constant, that means that our change in volume is 0. And because work is equal to negative pressure multiplied by our change in volume, if the change in volume is 0, non-existent, that means that work will also be 0. All right. Now, this isn't always the case, but for most chemical reactions we set up, which take place in the solution phase, the change in energy for that reaction is simply equal to the change in thermal energy that reaction experiences, whether it's endothermic or exothermic. All right. And this expression holds true when our volume is constant. All right, so under most circumstances, we can simplify our expression down to thermal energy release is equal to the energy released by the reaction. I should say released or absorbed. Now, when it comes to determining the change in energy for a reaction under constant volume, we can do this simply by looking at the change in thermal energy. And this leads us to a topic that sounds way more exciting than it is. This is called bomb calorimetry. Bomb calorimetry sounds explosive. Sadly, that is not the case, because a bomb is a vessel. The bombs that I've worked with in the past are usually made of thick insulating Teflon. It's just simply an insulating vessel. Insulating vessel is the bomb. All right, and there is usually a way to monitor temperature. Whoa. That's poor drawing even by my standards. Here, let's get a better thermometer up in here. All right, so there's a way to monitor the change in temperature. And so we've got some temperature, and usually inside, when you're doing bomb calorimetry, there's going to be a reaction vessel inside. So this right here is a reaction vessel, All right, so we actually set up our reaction in here. It's jacketed by water. So this is all H2O. All right, to absorb the energy released, or to give the reaction energy if the reaction's absorbing it. And then we have our thermometer. Now, it starts at some initial temperature. Now, to measure the change in energy for this reaction, and to do so thoroughly, as the reaction releases energy into the vessel, two things are going to increase in temperature. All right. As the reaction goes and starts releasing energy into its surroundings are obviously composed of water, right? So the change in energy for this reaction will be equal to the thermal energy absorbed by the water. But that's not the only thing absorbing energy. The bomb itself will also experience the same temperature increase as the water that surrounds the reaction vessel. So the thermal energy for this reaction is going to be equal to the change in energy of the water plus the change in energy of the bomb itself. Let's see. Okay, we got a question. Is there a way to actually calculate the volume? To calculate if the volume is not constant? Yes. Total. Okay. So Raj's question is there a way to calculate the change in energy for a reaction if a volume is not constant? There totally is. If you look back at the equation that we wrote out, if your volume is not constant, then the change in energy for your reaction is going to be equal to the thermal energy released plus the energy transferred through work. So if your volume is not constant, then you're going to have two things to calculate. First, the Q of the reaction and the work performed either by or on the reaction. So you'd have to check out both of those things. It is possible, but usually when we're doing bomb calorimetry, as we are in this reaction or in this example, reactions are chosen whose volumes do not change. That way, we can just look at the simple change in thermal energy. Hopefully that answers your question. All right, so anyways, because we have two things that are experiencing a temperature change, the water that jackets the reaction vessel and the bomb calorimeter, we have two calculations to make. Are we only, okay, there's another question from Sarah. Are we only working with constant volumes in this chapter? Not exclusively. In this section of the chapter, yes. When we're talking about bomb calorimetry, we will be working with constant volumes. There will definitely be examples where the volume isn't changing, as we saw last lecture. All right, so now with the Q's we've been dealing with up to this moment in time, we've been dealing with specific heat. One nice thing about doing a bomb calorimetry experiment is the bomb itself has a constant mass, and so we'll actually not be using the specific heat capacity, but just the heat capacity. The Q thermal energy transferred to the bomb is equal to the heat capacity of the bomb times the change in temperature. We don't have to worry about the mass because, again, bombs are just a standard piece of lab equipment. They don't change mass, and so every bomb comes with a measured heat capacity, and so you don't have to measure the mass. It's just all included in that package. So let's do an example of bomb calorimetry. Oh, goodness. Come on, song of the day, we want smooth sailing. There we go. All right, so let's take a look at the following example. So in this example, we have 1.010 grams of sucrose is burned in a bomb calorimeter. The initial temperature is 24.92 degrees C. Let me just get rid of this little dot right there so that we don't confuse our decimal points. The final temperature is 28.33 degrees Celsius. The specific heat, or not the specific heat capacity, the heat capacity of the bomb calorimeter is 4.90 kilojoules per mole. All right, and then we're asked to determine the change in energy for this reaction. All right, now we're told that this reaction happens in a bomb calorimeter. That is an automatic signal. So right here, whenever you're doing bomb calorimetry, we know that the reaction is taking place under constant volume. So we know that the change in energy for our reaction is equal to just the energy, the thermal energy transferred. We do not have to worry about work in this scenario. We do have to worry about the two things that are going to be absorbing energy in this reaction. Now, we've been given energy. Okay, I jumped the gun a little bit. I was so excited. Is this example exam caliber? So we had we have a question. Is this example exam caliber? This is, for bomb calorimetry, this is about what you'd be seeing on the test if it were just a bomb calorimetry problem. Also, I jumped the gun a little bit. I asked us to, right here, to determine the energy of the reaction, and here I forgot to tell us a couple of key components that we need to solve this. We know that the change in energy for the reaction is equal to the change in thermal energy for the reaction, but here we're dealing with the energy absorbed by the calorimeter. Oh, goodness. Plus the energy absorbed by our water. And you'll notice that I was so eager to get to the end of this problem that I forgot to write down the information about H2O. So the mass of water that we're dealing with here is 500.0 grams, and the specific heat of water, as always, is 4.184 joules per gram degrees Celsius. All right, so now we have enough information to solve the problem. We need to go after two things, and those things are the energy absorbed by the calorimeter and the energy absorbed by water. The sum of those things will be the change in energy for this reaction. So first, we know the energy absorbed by our H2O is going to be equal to the mass of water times the specific heat of water times our change in temperature. We need to calculate our delta T, and as always, we know that it is the final temperature minus the initial. All right, so our final temperature is 28.33 degrees Celsius. Our initial temperature is 24.92 degrees C. All right, and when we, oh goodness, when we crunch the numbers on this situation, we have 28.33 minus 24.92 gives us a change in temperature of 3.41. Now we know that that's the value that our calculator is giving us, but let's look at our significant figure situation. Our first temperature is precise to the second decimal place. Our second temperature is precise to the second decimal place, and we know, since we're doing a subtraction, that our answer's significant figures must reflect the least precise number, and so it must have a significant digit in the second decimal place, as this change in temperature does. So there's no need to round or add any decimals. Now we're ready to calculate the energy of our water, and we have a mass of 500.0 grams. We have a specific heat capacity of 4.184 joules per gram degrees Celsius, and we have a change in temperature of 3.41 degrees C. Whoa. These are a little cramped here, but that's why lasso tools are awesome. I wish whiteboards came with them. Sorry, I'm overly pleased with the application of the lasso tool there. Anyways, so where were we? Okay, we're about to crunch our numbers for H2O. Before we do, let's just take a look at our units. Grams cancel grams, degrees C cancel degrees C. We're left with joules, which is good because we're calculating an energy. So we have 500 times 4.184 times 3.41 gives us a value for temperature of water, a value of 7,133.72. That's our correct value. Now let's look at how many sig figs we can have. We have 4 for our mass. We have 4 for our specific heat capacity, but our delta T only has 3. So we can only have 3 significant figures in our number. I'm going to wait to round to the end of the calculation, but I'm putting these lines here to remind myself that I only have 3 significant figures for the thermal energy absorbed by water. Now let's take a look at the thermal energy absorbed by the bomb. Oops. There we go. Thermal energy absorbed by the bomb. Now this is a lot simpler. All we have to do is punch in our heat capacity for the bomb, which is 4.90 kilojoules per degrees C. We've already calculated our delta T, so we can plug that in right here, 3.41 degrees Celsius. Our units are going to cancel, degrees C with degrees C, and now we punch in our numbers. We have 4.9 times 3.41. It gives us a value of 16.709. Again, we can only keep 3 of our significant figures. I'm going to wait to round till the end. And our units here are an energy unit, which is good, the only unit left standing, which is kilojoules. Now, the last step of this problem will be to add our energy absorbed by water and the energy absorbed by the calorimeter itself. Before we can do that, though, we have a problem. The specific heat capacity for water gave us an energy in joules, and the heat capacity for our bomb calorimeter gave us an energy unit in kilojoules. Okay, Macy, I see your question. How come the units changed? It's actually due to the fact that the heat capacity of the calorimeter and the heat capacity of water were given in different units. So we have to take these two, and we're going to have to either convert kilojoules to joules or joules to kilojoules before we add these together. It's something to watch out for when you're doing problems like this. So I'm going to take, it doesn't matter which one you convert. I'm going to convert my joules to kilojoules. So that was, oh wait, now I just forgot what the number was. All right, so my Q of H2O was it did I write kilojoules per mole in the question? Let's see, it was kilojoules. Okay, hang on one second. So Macy's asking why it was written as kilojoules per mole in the problem. Let me take a look. Oh my gosh. Okay. Thank you for your sharp eyes. Okay, so Macy's question is, why is this kilojoules per mole? And the answer is, I messed up. This unit should not be kilojoules per mole. It should be kilojoules per degree C. So thank you for that catch. I apologize for the confusion later. The confusion that this may have caused earlier in the thing. Let's see, we're having a couple more questions crop up. Okay, yes, conversions for joules are the same as grams and milliliters, just because you use the same metric prefix system. All right, so after that, detour, let's take a look. So we have our Q of H2O is equal to 7,133.72 joules. And we want to convert this to kilojoules. So we want joules to cancel. It goes in the denominator. We want to be left with kilojoules up in the numerator. 1 kilojoule is 10 to the third joules. So joules cancel. And our energy absorbed by water will be 7.13372 kilojoules. Now, sig figs wise, let's take a look. We had 3 significant digits in our calculation for the energy absorbed by water. So after the unit conversion, we can only have 3 significant digits. Now we're ready to calculate the change in energy for this reaction. It's equal to the amount of energy absorbed by water plus the amount of energy absorbed by the calorimeter itself. And we have 3 significant digits in our energy absorbed by water, and we also have 3 significant digits in the energy absorbed by the calorimeter. So adding these 2 together, let's see, plus 7.13372 gives us a value, gives us the value for our answer is 23.84272. When we look at the significant digits here, we're doing addition subtraction. which means we look at the last significant digit in each number, and we have to roll with whichever is less precise. In this case, the thermal energy absorbed by the calorimeter is less precise, therefore we need to round to that first decimal place. So our final answer will be, for the change in energy for this reaction, will be 23.8 kilojoules. And that is our final answer. Any questions so far? Okay. All right. So bomb calorimetry is a very useful technique. You can use it to determine the amount of energy released or absorbed in a chemical process. The only difference, if energy were absorbed, is the temperature is going to drop as it sucks energy out of its surroundings into the system. Do we convert it to kilojoules or? Okay, we do have a question. Vraj is asking, do we convert to kilojoules or joules? And the answer is, you could go either way as long as the units are the same. Totally. If the problem specified, find the delta change in energy in kilojoules or joules, then you have to roll with that. But if it doesn't, as long as the units are consistent, that's all that matters. Okay, so like I said, bomb calorimetry, you can, totally depends on the question. You can determine the amount of energy absorbed or released by a chemical reaction, but you can only do that for a specific mass. One of the downsides to change in energy for a reaction is, for example, we calculated the amount of energy that would be released if we burned 1.010 grams of sucrose. But what if we burned 20 grams of sucrose instead of 1.1? It would be a different quantity, right? Delta E of a reaction is specific to the amount that you're using in that reaction, all right? Now, a more useful quantity than the change in energy for a reaction is something we call, oh goodness, hang on. Need to open a new layer. Here we go. Is something we call the change in enthalpy. Oh, okay. Let's see. Someone's asking, is there a second part to this question? No, actually, I'm not ambushing you. That question was just a straightforward thing. That's all there is to that. Now, the change in enthalpy is abbreviated with the symbol delta for change in, and then H. And delta H is far more useful than the change in energy for a reaction, because the change in enthalpy for a reaction is equal to the change in energy per mole. Change in enthalpy is a ratio of the amount of energy absorbed or released by the reaction and the moles of reactants used in that reaction. And because it's a ratio, it's a lot more versatile. It's more useful. You can talk about the combustion of sucrose and its delta H without specifying the quantity, because, again, this is a ratio here of energy per mole. Typical units for delta H is, can be measured in any energy unit, but it's commonly seen in kilojoules per mole or kcals per mole are the two most common ones. In Gen Chem, we typically stick to kilojoules, but in OChem, it's very, very common to see this listed in kcals per mole. Let's see. Did we not need to include the mass of our sucrose? Okay. So there's a question about the bomb calorimetry. In the previous calculation, you actually didn't need to use the mass of sucrose. It's more there just to say that with this quantity, this amount of energy is released. But the beauty of the bomb calorimetry experiment is you don't have to, all you have to measure is the change in temperature, and that's enough to calculate it. Yeah, okay. So Sulai, your comment is, so we would convert the mass of sucrose to moles to find the delta H with that. That is absolutely correct. Once you combine the information gathered from a bomb calorimetry experiment and the mass of sucrose, you could calculate the change in energy of sucrose given its molecular weight. That's exactly where that was headed. And honestly, the reason why you do calorimetry is to calculate the change in enthalpy for a reaction. So that's the reason that information is included, and you can see in future examples, how the previous problem will be combined with what we're learning now. Excellent observation. All right, now, so we're talking about change in enthalpy for reactions, and just laying down a couple of what's the word I'm looking for? Just incorporating some vocabulary and helping us to understand what the values of delta H mean. If you have a change in enthalpy that is positive, much like change in energy, if your delta H is positive, that means your reaction is, not exothermic. It means it's endothermic. Energy has been absorbed. And if your change in enthalpy is negative, that means that your reaction is exothermic. Energy has been released. So the same intuition that we have for delta E, change in energy, and also change in thermal energy and work, positive is endothermic, negative is exothermic. One interesting facet of change in enthalpy, I'm going to give myself a little more room on this slide. Is how delta H integrates into balanced chemical equations. Let's say that you have a chemical reaction. We're going to get a little symbolic here, but bear with me. Where we have two reactants A and B reacting together to make a product C. All right, and let's say I told you that this process, this reaction, is exothermic. All right, now that means that energy is being released, and if energy is released, in essence, it's produced by this chemical process, right? It's released by this chemical process, and you can treat energy as if it is a product of this reaction. And the cool thing about delta H is because it is a ratio between change in energy and moles, right? Change in energy per mole. You can incorporate it. You can write the value of your change in enthalpy directly into the chemical equation, just like you'd write any other product. All right. So if this reaction is an exothermic, A reacting with B produces product C, but it also produces energy, and we can write that on the product side. Conversely, if we have a reaction that is endothermic, all right, let's just say we have a different reaction where A plus B produces a product D, all right, so a different chemical reaction. Maybe I should use a different, instead of B, we'll say A plus C goes to D. If we're dealing with an endothermic process, as we are here, that means energy is absorbed or consumed in this process. As a result, for endothermic processes, you can write delta H for your reaction as a reactant because essentially it's consumed by this process just like A and C are, right, and converted to D. So for exothermic processes, our delta H is written on the product side. For endothermic processes, you can write delta H on the reactant side. And using this knowledge, we can now incorporate energetic quantities into stoichiometry problems like the following example. So consider the following example. The combustion of methane gas with oxygen gas produces carbon dioxide gas and water vapor. Oh, let's see, we're getting a question. Is that always the case, or are there any exceptions? Is that always the case that delta H can be incorporated into a reaction as either a product if it's exothermic or a reactant that it's endothermic? Yes, that is always the case, zero exceptions. So in this example, we're reacting with methane and oxygen combusting to make carbon dioxide and water. So let's take a look. Part A would be write a balanced chemical equation. Part B would be listed as the following. Switch to black. The change in energy, or enthalpy, for this reaction is equal to negative 802.3 kilojoules per mole. Period. If 57 kilojoules are released, how many grams, that is not how we spell how many grams of methane combusted? All right, so first off, we have a equation to balance. So we have, let's see, we've got, methane plus oxygen producing CO2 and water. All right, first off, we have carbon, hydrogen, and oxygen. On our reactant side, 1 carbon, 4 hydrogen, 2 oxygen. On the product side, 1 carbon, 2 hydrogen, and then 2 plus 1. The 2 oxygen coming from carbon dioxide and the 1 coming from water. All right, now whenever you're balancing chemical equations, you always want to take the path of least resistance, and the easiest two to balance here seem to be hydrogen, right? 2 goes into 4 evenly. We need 2 hydrogen on our product side, so we have to multiply H2O by 2. This balances our hydrogen and changes our oxygen count. Now we have 2 plus 2. All right, carbon's balanced, oxygen is not. We have a total of 4 on our product side, only 2 on our reactant side. So we need, hang on, cancel. So we need 2 oxygen on our reactant side. Now we have 2 times 2, which is 4 atoms of oxygen, and our reaction is balanced. All right, so that is part A. Part B for this reaction is first, well, here. Before we start anything, let's identify what we are trying to find. All right, we are trying to find how many grams of CH4 combusted. All right, and so that's what we're after. Let's look at what we're given. All right, we are given that, let's see, we're given that we produce 57 kilojoules of energy, and we're told that our change in enthalpy is negative 802.3 kilojoules per mole. All right, the first thing you want to do anytime you're given a change in enthalpy in a stoichiometric context is you want to incorporate it into the chemical reaction you're dealing with. And to do so, we have to look at the sign. This change in enthalpy is negative, which makes it an exothermic reaction. And if this reaction is an exothermic, that means energy can be treated like a product. Now, when you write this energetic quantity into the balanced chemical equation, you do not include the sign. Whether it's negative or positive, you always write it in as a positive value. The sign for delta H is simply telling you which side of the reaction to place it on. So this is 802.3 kilojoules. But you do not write it as a negative value. All right, the negative value tells you that you put it on the product side. Now, also you'll notice when you write this into the chemical equation is you'll notice that we shed the per mole. All right, the per mole in the delta H is something we call this is something we call a reaction mole. And that means you can only, what this means is it's telling you explicitly to only place this in a balanced chemical equation. All right, you place it in a balanced chemical equation. It's already, and once you do that, it's already in an energy to mole ratio, right? Everything else in this balanced chemical equation, whether we're talking about methane, this is 1 mole, right? We've got 2 moles of water producing 1 mole of carbon dioxide, 2 moles of oxygen on the reactant side, producing 2 moles of water on the product side. And then we have energy as the unit. So the energy per mole is already incorporated once you place it into the balanced chemical equation. So you write it in as 802.3 kilojoules. The fact that it's in a chemical reaction already places it or incorporates the per mole quantity in the unit. Hopefully that makes sense. I'll keep an eye on the comments to see if there's a flood of questions. All right, once we've incorporated the sorry, I lost my train of thought, the change in enthalpy into our chemical reaction, now we can set up, we can determine how many grams of methane is produced, all right? And here's how we're gonna do that. Here, give me 1 second. I kind of messed up my slide, so I need to do a little bit of slide surgery really quick. Again, lasso tool to the rescue. All right, now let's go to a new okay, sweet. There we go. Control paste. Okay, that looks hideous, but correctable. Okay. Now we can zero that out. All right. And we're almost back to normal. Okay. Oh, goodness. Sorry about that. Here's where the song of the day is failing me here. Okay. Okay, sweet. Okay. Sorry for those technical difficulties. We're back. I have control of my screen again, and we're ready to rock and roll. Okay. So we have just incorporated our change in enthalpy into our chemical equation. We can now use the energetic quantity we were given to find the amount of grams of methane that were combusted in this chemical process. Here's how. If I told you that you had 5 grams of water and you were asking, and I was asking you to calculate how many grams of methane were combusted to produce 5 grams of water, you could do it, right? You'd take moles of water or grams of water, convert to moles, and then use the mole to mole ratio to go from water to methane. Here, I haven't given you water, I've given you energy. So we need to use the energy to mole ratio in this chemical equation to accomplish the same task. We want to put energy units, kilojoules, in the denominator. We want to put moles of methane in the numerator. And actually, I shouldn't put a 1 there. Now, the ratio between moles of methane and energy, we read directly out of the chemical equation. 1 mole of methane combusted produces 802.3 kilojoules of energy. That ratio comes directly out of the chemical equation. Energy units cancel. All right. And now we have moles of methane. We need to convert from moles of CH4 to grams. Ooh. Right. Carbon has an atomic mass of 12.01. Hydrogen, 1.008. We have 4 of them here. So we have 1.008 times 4 plus 12.01 comes out to be 16.042. Using the significant figures that I've used, I'd be limited to the second decimal place. So 16.042 is my mass. 4 sig figs in that number. Now moles of methane cancel moles of methane. and we're good to crunch our numbers. 57 divided by 802.3 times 16.042 gives us a value of 1.13971582. All right, it keeps going, but we don't have to. As far as significant figures are concerned, we're limited to 2 by our initial energy. That 3 is going to round down, so our correct value with the correct sig figs will be 1.1, and then our units are grams of methane, and that is our final answer. So anyways, this is our first example of how we incorporate energetic quantities into stoichiometry, and our bridge that allows that to happen is our change in enthalpy. Okay, so I have a question in the queue. What if it was water? I'm assuming that question means, what if I were to ask you to determine how many grams of water were produced if 57 kilojoules were produced? And the only difference really would be you would have moles of water in the numerator instead of moles of methane, and it would be 2 moles of water instead of 1 mole of methane because there's a 2 in front of the H2O. All right, this is too easy for a test question, right? You are absolutely correct. Absolutely correct. Too easy for a test question, but this was kind of our first example of a question using change in enthalpy. So the questions will build excuse me. The questions will build complexity as we go, but this was kind of like our dipping our toes in the water, so to speak. All right, other questions about this first example. All right. So we are about to take a deep dive into doing a ton of different things with change in enthalpy. We're going to learn many ways to calculate change in enthalpy. It's going to be, I'm excited to hit this part of the chapter. Not gonna lie, it's probably my favorite part of chapter 6. That being said, before we do, we need to kind of lay down or develop the relationship between a chemical reaction and the change in enthalpy. So, oh goodness, I'm about to show you how to relate, or I should say, relating change in enthalpy to chemical equations. And I'm about to write out a few expressions highlighting how change in enthalpy relates to chemical equations, and how changing a chemical equation will change the delta H for the expression. Now, this may seem a little random at first, and you may not understand and it may seem a little abstract. You may not understand the reason why we're doing this, but trust me, hang on. There's 3 relationships that I want to highlight, and then once we've written them down, we'll explore how we can use these relationships to calculate change in change in enthalpy for different reactions. But we just got to get through these. So if they don't make a lot of sense, hang on. Once you get out the other end, we'll start using these in a few examples to actually calculate delta H. All right, but before we dive in, let's see, I've got a question from Diana. So the change in enthalpy in a reaction can be used to find any mass for a reactant or product. Yes, that is correct. You can use change in enthalpy in conjunction with, if you know the amount of energy released, let's say maybe in a bomb calorimetry problem, you can use that to find any mass for the reaction if you know the delta H already. That is 100% correct. All right, so we're going to develop 3 relationships between delta H and a changing chemical equation. And so anyway, so here they are. So first, consider a reaction between a molecule that I'm going to call A and two molecules of B that produces 3 molecules of our product C. And I'm going to say that this has a delta H. We're just going to call this delta H1 because it's the change in enthalpy that accompanies reaction number 1. All right, now consider a second reaction, calling this reaction 2. Let's say in the second reaction, 2 molecules of A react with 4 molecules of B to produce 6 molecules of C. And this reaction has a change in enthalpy we're going to call delta H2. Now the relationship you'll notice between the first reaction and the second reaction is that all the stoichiometric coefficients are doubled, right? They're all doubled. As a result, the change in enthalpy for the second chemical equation will be equal to 2 times the change in enthalpy of the first equation, all right? If you multiply every species in a reaction by some number, in this case by 2, the change in enthalpy for the new expression will also be multiplied by the same number. It'll be the delta H of the original times whatever number you choose to multiply. So there is our first relationship between a changing chemical equation and delta H. Consider now a second situation. Let's consider a reaction that I'll call reaction 1 that involves 1 molecule of A reacting with 2 molecules of B to produce 3 molecules of C, and this has a delta H that I'm going to call delta H1. Now consider a second chemical reaction, one in which you have 3 molecules of product C that decompose into 1 molecule of product A and 2 molecules of product B. You'll notice that in this chemical, when you compare reaction 1 to reaction 2, that the difference is the product of reaction 1 is the reactant in reaction 2. And you'll notice that the reactants in reaction 1 are the products of reaction 2. So these two reactions are the flip of each other. You flip products and reactants. And the change in enthalpy for the second reaction is the flip of the change in enthalpy for the first reaction. And how that is signified is it is equal to the change in enthalpy of the first reaction multiplied by -1. All right, is the negative, is the opposite of the first, the change in enthalpy for the first reaction. So anytime you flip a reaction in reverse, you exchange reactants and products, the change in enthalpy is the same, except it's multiplied by -1. All right, those are our first two relationships. The third and final relationship between the change in enthalpy of a reaction and the reaction itself can be seen here. So here's our third and final relationship. Consider a reaction that, again, I'm calling reaction 1, that involves A reacting with 2B to produce 3C. And this has a delta H that we'll call delta H1. Consider a second reaction. It's reaction 2. And this is a reaction where 3 molecules of C rearrange into react to produce 2 molecules of D. And I'm going to call this delta H2. Now you'll notice that we have 3 molecules of C on the reactant side of reaction 2 and 3 molecules of C on the product side of reaction 1. And you'll remember from the time that we've spent in redox that if we add these two together, that if you have a species both on the reactant side of one reaction and the product side of another, that these two cancel each other out. So adding these two reactions together, we would get a new expression. A plus 2B produces 2D. This is a completely new chemical equation. This is a new reaction that I'm calling reaction 3. All right? And the change in enthalpy for reaction 3, because this reaction was the sum of reaction 1 and reaction 2, that's exactly how you calculate the change in enthalpy for reaction 3. This is the sum of the change in enthalpy for the first reaction plus the change in enthalpy for the second. So anytime you add two reactions together, the change in enthalpy for the new reaction is the sum of the individual delta H's for those two chemical processes that you added together. All right, now, this was all very abstract, and before we start applying these, it's going to get a little more abstract. All right, so delta H, so this brings us to something called Hess's Law. Hess's Law. And Hess's Law is money. This thing is pure gold. Because, oops, goodness gracious. There we go. Hess's Law tells us that change in enthalpy, delta H, is something called a state function. Delta H, change in enthalpy, is a state function and is therefore independent of path. Is therefore path independent. All right. Delta H is a state function and is therefore path independent. Now, what does that mean? All right. Let's talk about this. Let me give you some examples. So for example, what are some good examples of state functions? A great example of a state function is being at a concert. Being at a concert is totally a state function. All right? There are multiple ways to get to a concert, right? There's ticket presale, right? There is a general. You could have a general sale. You could get a ticket through StubHub. You could buy one off a scalper and destroy the industry that you love so much. You could sneak in and not support your artists and also destroy the industry that you love so much. All of these are different ways of getting to a concert, but once you're at a concert, being at a concert, it doesn't matter how you got in. We're all there. We're all enjoying the same concert, right? Getting to class, being in lecture is another example, right? If we're all, this is an ironic thing to be talking about on our first day of digital lecture, right? If we're all in the same classroom, it doesn't matter how you got here. We're all in lecture. It doesn't matter if you rode your longboard or drove or rode a bike or walked or paradropped in if you have that capacity. Once we're all in the same room, it doesn't matter how we got here. We're all in the same lecture, experiencing the same thing. Being in lecture is a state function. Being at a concert is a state function. Getting to lecture is not a state function, all right? Getting to lecture is path dependent. Getting to a concert is path dependent, how you buy the ticket, how you arrive at the show. But being there is a state function. And basically, the brass tacks of what Hess's Law tells us is that it does not matter. It does not matter how you calculate it. It doesn't matter how you calculate your delta H. Once you know, you know. Because the delta H for the formation of water delta H, the change in enthalpy for the reaction that forms water, will always equal the delta H for the formation of water. Because water is always the same. It doesn't matter how you calculate delta H. Once you get it, once you know, you know. And so there's a variety of different attacks, different approaches we can take to calculating delta H. And once we get there, we're there. All right. Now, that was a little abstract, following an abstract kind of me writing abstract relationships between how delta H changes as you manipulate a chemical equation. Why are we looking at any of this? You may be asking, and we're gonna bring it all back home in this next example. So consider the following example. First, I'm going to give you a series of combustion reactions. Whoa, not in yellow. So the combustion of solid carbon, so that's solid carbon reacting with oxygen gas, produces carbon dioxide, and this is a change in enthalpy of negative 393.5 kilojoules per mole. All right. Consider the combustion of carbon monoxide gas. CO gas can also be burned. 2 moles of carbon monoxide combust with 1 mole of O2 gas to produce 2 moles of carbon dioxide. This is a delta H of negative 566.0 kilojoules per mole. All right, and consider a third combustion reaction, and that is the combustion of hydrogen. We've seen this one before, with oxygen to produce H2O. This combustion has a change in enthalpy of negative 483.6 kilojoules per mole. All right, now, each and every one of these reactions, combustion reactions, are very, very fast. They're exothermic. It's very easy to measure the change in energy associated with all of these reactions. We can all measure these with bomb calorimetry. All right, we can measure the change in energy and then divide by the moles of limiting reagent, and we get a delta H for each one of these. Now, so that's all set up. You may be wondering, what are we going to do in this problem? In this problem, we are going to calculate the change in enthalpy for the following reaction. And this reaction is the reaction between solid carbon and water vapor to produce carbon. Oh, do a cleaner job. Carbon monoxide gas plus hydrogen. All right. Now, this reaction is not this reaction is not an easy reaction to study. This thing is slow. All right, this is slow, it's sluggish. This is not a reaction that we could effectively throw in a throw in a bomb calorimeter and measure the change in enthalpy for this reaction. It's very slow, it's very sluggish, it's a difficult reaction to study. But we can use these three reactions and the fact that change in enthalpy is a state function. It doesn't matter how we calculate it as long as we get there. We can use these three reactions and the relationship between delta H and manipulating the reaction, changing the reactions to calculate the delta H of this reaction. All right. Now here's the strategy. So hang with me here. What you want to do is you want to look for each reactant and product in the given reactions. All right, so first we want to identify where each one of these reactants, solid carbon, water vapor, carbon monoxide, and hydrogen gas. I'm going to number these. 1, 2, 3, and 4. We want to identify where these species are in our given reactions. All right. So, for example, first, solid carbon, right here in our first chemical equation. All right. Water vapor. Let's see. Water vapor is produced in the third one. There's number 2. Right there. Carbon monoxide is in reaction 2. All right. And hydrogen gas is in reaction 3. So we've identified each reactant and product in the given reactions, those combustion reactions that we started with. And then second, what we want to do once we've identified where those are is you want to manipulate the given equations to place the reactants and products on the correct side of the equation with the correct stoichiometric coefficients. All right. On the correct side of the equation with the correct stoichiometric coefficients. So once we do that, we're going to be able to add these reactions up and calculate our delta H. All right. I'm going to have to link to another slide. We're going to be a little bit low on space, so you may want to pop back here to reference the reactions that were given. So let's remember first, we're after this chemical equation. We're after solid carbon reacting with water vapor. Hang on. Solid carbon reacting with water vapor to produce carbon monoxide plus hydrogen gas. All right, this is the chemical equation that we're after. Oh, here, hang on, we're getting did you just number? Okay, carbon monoxide, yeah, I numbered 3. I'm gonna renumber them right up here. So we've got solid carbon, I numbered 1, water's numbered 2, carbon monoxide 3, and H2 is numbered 4. Okay. All right, so this is the equation we're trying to calculate. Now first, in our first reaction, we've got, oops, I'm gonna put this here. In our first reaction, we've got solid, ooh, don't want that in red. We've got solid carbon reacting with oxygen gas to produce carbon dioxide. And this is a delta H of negative 393.5. Oops, I need a little more space. Delta H of negative 393.5 kilojoules per mole. All right, and you'll notice in this first reaction, we have correctly placed our first reactant. We want solid carbon on the reactant side of the equation. It's on the reactant side of this equation. We can leave this reaction as is. This thing is good to go. Now, let's look at our equations now to identify where we want to place, or where can we find water. All right. Now you'll notice that water is present in our final equation, but we have a problem here. Here we have the equation 2 moles of H2 plus 1 mole of O2 gas produces 2 moles of H2O, and that this has a change in enthalpy of negative 566.0 kilojoules per mole. All right, now we've identified, so we're looking at our second reactant here, that we have water in this equation, but there's a problem. It's on the reactant side. All right, so to place we want water on our reactant side, but it's on the product side of this equation. So to place this reactant properly, we need to flip our reactants and our products for this equation. So we're going to exchange. We're going to rewrite this as 2 molecules of water decompose to produce 2 molecules of hydrogen plus 1 molecule of oxygen. And I'm going to need to use my lasso tool again. Now the delta H for this new reaction, whenever you flip a reaction, it's going to be the same, but with an opposite sign. And our original was negative 566.0 kilojoules per mole. But because we flipped our reactants and our products, we have to multiply this whole thing by a negative 1. Total. Okay, I see a couple of people commenting that they got to leave soon. Next live class is at 1. I'm going to finish this problem, but the lecture will stay on YouTube, so you can come back and watch to see the conclusion. But I just would rather finish this problem than leave everything hanging. All right. So, oh, sorry. Viraj is pointing out, this is my second faux pas, our delta H for the reaction with water is negative 483. Oops. I apologize for that. 483.5 0.6, 0.6. So here our delta H, now once we flipped our reaction, is equal to a positive 483.6 kilojoules per mole. Totally. Okay, now, so we have number 2 placed on the correct side of the reaction, but there's a second problem, and that is the stoichiometric coefficient. In this reaction, we have 2 molecules of water, but in the reaction we're trying to calculate, there's only 1. So we need to multiply everything in this reaction by 1/2. That way we only have 1 mole of H2O, and if we're multiplying everything in our reaction by 1/2, that means we also need to multiply our delta H by 1/2. Once you do this, once you multiply the whole thing through, you're going to get one mole of water vapor decomposes into 1 mole of H2 gas plus 1/2 a mole of O2 gas. And the delta H for this expression will be 483.6 divided by 2 is 241.8 kilojoules per mole. All right, now you'll notice that we've successfully placed our second product on our reactant side with the correct stoichiometric coefficient. In addition, we've also correctly placed number 4, our second product, number 4, H2 gas, with the correct stoichiometric coefficient on the product side of this reaction. All that's left then is we need to find carbon monoxide. And to do that, we'll look at the third and last reaction that we have yet to use. So carbon monoxide, number 3, is present in our second chemical equation, and that's 2 moles of carbon monoxide reacting with 1 mole of O2 to produce 2 moles of carbon dioxide. And this combustion, here's where our negative 566 comes into play. 566.0 kilojoules per mole. All right, now carbon monoxide, number 3, needs to be on the, yeah, it is proportional to CO2. Needs to be on the product side of this reaction. So again, we're going to flip our reactants and our products. So 2 moles of CO2 decompose into 2 moles of carbon monoxide plus 1 mole of O2 gas, and our delta H here is equal to our previous delta H, 566.0 kilojoules per mole multiplied by -1. All right, now we have carbon monoxide, I underlined carbon dioxide. We do have carbon monoxide on the product side of the equation, but we need to have a stoichiometric coefficient of 1. So again, just like the last problem, we're going to multiply everything in this reaction by 1/2, including our value for delta H. And that will bring carbon monoxide right around to where we want it to be. All right, so we have our final reaction we need to complete this process. Carbon dioxide gas producing 1 mole of carbon dioxide producing 1 mole of carbon monoxide plus 1/2 O2. Oops. There we go. Now, we've placed carbon monoxide number 3 on the correct side of our chemical equation. We have a delta H here. It's going to be 566 divided by 2 is 283.0 kilojoules per mole. And so I want to point out a couple things now that we're here. Again, the point of doing this is we want a reaction where we get solid carbon reacting with H2O, producing carbon monoxide gas and hydrogen gas. And we have those. We have solid carbon and H2O, both on our product side with stoichiometric coefficient of 1, producing H2 gas and carbon monoxide. That's what we want in our final answer when we add this up. But in addition, we need to make sure that all the other species in this reaction cancel. To cancel, we need to make sure that we have the same amount on both the products and reactant side. And you'll notice that we have 1 mole of carbon dioxide on the reactant side of our third equation, and we have 1 mole of carbon dioxide on the product side of our first equation. These two cancel each other out. In addition, and for those of you who were uncomfortable by the 1/2 O2, you're like, 1/2 O2 is never allowed in a balanced chemical equation. That's totally true. But here these are just placeholders. We're allowed to introduce fractions into our balanced chemical equations as long as we get rid of them at the end, right? And you'll notice that we have 1 mole of oxygen gas on the reactant side of our first equation. And then in equation 2 and 3, we have 2/2, which is also equal to 1 mole of oxygen gas. So these 2/2 cancel with this 1 mole, and what's left? Solid carbon reacting with H2 gas to produce carbon monoxide plus, H2O gas on the reactant side, producing carbon monoxide and H2 gas on the product side. And the delta H for this reaction is equal to the sum of the 3 delta H's we determined in our previous steps. Okay, great question. I'm getting a question here. What if the reactions don't add up, or do they always add up? So here's the thing. In this problem, we were asked to calculate the delta H for solid carbon reacting with H2O to produce carbon monoxide and hydrogen gas. So in order to do that, all of the other things, all the other components of the reaction must cancel, all right? They have to cancel. If they don't, then there's going to be other reactions given in the problem that will allow you to cancel them. Does that make sense? So you will always have enough information to not only place the reactants and products that you need for your reaction, but also to cancel all the other things that don't belong in the final answer. All right, let's take a look at, let's actually get a value for this delta H. So we have negative 393.5, all right, plus 241.8, plus 283.0. All right, these add up to my value is 131.3. When we look at significant figures, you'll notice that each of these numbers that we added have their last significant digit in the first decimal place. Our value has its last significant digit in the first decimal place, so we don't need to round or add any more decimal places so we have the correct value, correct sig figs, and now we have the correct units. The delta H, the change in enthalpy for this chemical equation, is 131.3 kilojoules per mole. So that is that situation. Oh goodness. All right. So any questions on this problem? All right. We went a little bit over today, but again, this stream will remain up and live on YouTube, so you'll feel free to re-watch. We will be streaming again on Wednesday, same time, 11:30 to 1. So anyways, thanks for dropping by. This was an interesting experiment. I'm sure it'll get more streamlined as we continue. Of course, you can hit me up with questions that you have through electronic means, and I will catch you all. I'll catch you all on Wednesday. Thanks for tuning in. Oh, I'm getting one question. Would you still give us equations on the exam? I totally will. You will totally have questions on the exam. Hang on. You'll totally have all the equations you need on the exam. Yes. Sorry. Questions are trickling in here. There's a little bit of a delay. Yes. This stream will be on my channel. Will be on this channel. Oh, that is a good question. So Diana is asking, how are we going to do exams? All multiple choice on Canvas? ? So I'm still here, so we can talk for a second. About exams. So exams. So here's a little bonus content after the lecture. So there's two possibilities. I guess I should say exam options. So possible exam options. This is something that I'm still working through, trying to figure out. It's possible to set up testing through through Canvas. You can totally do this. The other option is our take-home exams. And I'm still working through. I'm exploring the options, and I will give you more information as I have more information. One of the downsides to Canvas is it's multiple choice. Which is, as you know, is not my preferred style. Okay, sorry, I'm just making sure my thing isn't muted. Not my style. That's me being sad. Take-home exams are another option, and they would be they'd be more difficult. They'd be more difficult than the regular test because they'd be open everything, right? Open book, internet, other human, right? Open everything. So that's a possible, it's like me going, I don't know why my eyes are looking so weird. Question mark. In the event of a take-home exam, you would scan them and email them back to me, and I would email out PDFs. So that's how it would roll. I might roll with one or the other. I might do a hybrid of both, like maybe do a multiple choice section and then a written problem section. So I'm still kind of weighing options, figuring things out. Mostly, it will depend upon which kind of testing option I go with. Will depend upon how good the Canvas system is. Which I know it's good. I know people use it and stuff. I shouldn't say how good it is, but how much I like it, if that makes sense. So I'm going to be exploring that, seeing how. What kind of formatting options, if I want to do part multiple choice, part written take home. So I will have more information for that about that for you in the future. So we have another question. What about lab classes? So your lab classes are being run by your lab instructors. And so I know that all of the general chemistry lab instructors are kind of teaming, pooling resources, figuring out how they want to do things. There've been some talk about recording videos of them performing the experiments that you can watch. The last that I heard with your lab classes, you'll probably be given data sets and worksheets to finish. Obviously, you wouldn't be doing a pre-lab or whatever, but your instructors will probably be generating data sets for you to take and then do the calculations with. But I would, for specific information on what your specific lab instructor is choosing to do, you should contact them directly because again, each lab instructor has a final say over what they do in their section. So I know I've been part of the brainstorming process with that, but they're all functioning somewhat autonomously from the lecture side. So obviously you won't be attending lab class, but I would contact or wait for communication from your lab instructor as to the form that they're going to take. They may be assigning videos to watch and then handing out data sets for you to complete. Yeah, totally. So hopefully that answers the lab question. Oh, great question. Okay. What about the homework? So that is definitely in my purview. Oh, where did my little... There it is. Okay, right. So lecture homework. So let's talk about that. Oops. So lecture homework. Lecture homework is still assigned. And it is still due. It's assigned and due at the normal dates and times. Obviously, you can't physically hand them in. So the way to turn in the way I would like you to turn in your homework is you can email. With the homeworks, you can just email photos of your homework pages. Cool. That was a great question. Totally. For homework, email the pictures. Another great question. What about the ACS final? ACS final is a great question, and so let's talk about that for a minute. At least I can tell you where I'm currently at with that whole situation. The ACS final. Question mark? Sorry. One more homework related question. The question is, since people also write down, just the answers, is it okay to email a Word document? It is totally okay to email a Word doc or Google Docs. That is a totally acceptable way to turn in the homeworks digitally. All right, let's talk about the ACS final for a hot second. So I haven't had a chance to look at my emails this morning. So I'm a little, because I was prepping to get this whole situation set up. So I'm a little, so I haven't read if there's any recent alerts that have gone out. But the most recent email that I read said that classes are canceled. Oh, sorry. Answers are fine. Okay, so sorry. There's another homework question that I was responding to via text. Okay, so the most recent things that I've read have been that classes are no longer meeting, but I haven't read anything that has indicated how long that will go. I know other schools have canceled through the end of this semester. I don't know yet if FLC has. So I don't know if we'll be back in class and able to take the ACS final, or if we're going to remain digital for the rest of the semester. So in some sense, we have to wait and see. Oops, come back. Here we go. So if class resumes, it's totally on. So if class resumes, it's totally on. I can't resist. But if we have to stay digital through the rest of the semester, so if we finish digitally, so if we finish digitally, then we'll have to adopt alternate testing options for the final. Simply because there's no way to administer a sealed exam digitally, because you're not allowed to make copies of this thing, physical copies, so you're not allowed to make digital copies. So we would have to take a final that I would write. Let's see. Okay, we have someone weighing in that we who has a math professor said it was canceled till the end of the semester. If that is the case, then we will not be using the ACS final. We'll be using a final that I write, and again, the form that it takes will kind of depend upon what we end up rolling with. But you can rest assured that it'll be in a similar format to how we choose to test digitally for exam 1 and exam 2. So maybe Canvas take-home hybrid. We will have to see. But that is something that I'm actively trying to figure out. These questions have been awesome. Totally awesome. It's so this is weird. It's a weird form of feedback, because I'm sitting in a room by myself, talking into a microphone, and no one's here. So, but you're all here. But it's like we're all digital ghosts. Let's see. Some professors, personally, are not holding class for the rest of the semester. Not all, I think. Yeah. I need to. I'm not absolutely current on the most recent buzz, because my focus this morning has been making sure this thing went off without a hitch. Hopefully you found it enjoyable. If you could, let's see. This exam is easier than your exam, so you substitute. Okay, the question is, uh, uh, so here's the question. Since you said that the ACS exam is easier than your exams, so will the substitute exam be easier? Well, so just a bit of clarification, 2 points. One, I've been told by some students that the ACS was easier, and that's probably because it was all multiple choice. I can't really gauge whether or not the exam that you would take would be easier or harder. Mostly because it's just a very different. The form that I would take would be very different. It'd be like comparing apples to oranges. Because when you think about it, the ACS exam is here's 70 questions, 70 multiple choice questions. You've got 2 hours to take it. Whereas a final exam that I'm giving for a purely electronic class could be some multiple choice exam questions given through Canvas and a take-home portion. So it's really hard to gauge what's harder. Does that make sense? Because the take-home portion, you'd have more time, right? There's no way to really monitor time. So with a take-home exam, I would send it out to everybody and say, here, you've got 24 hours to take it, right? And send it back to me. So the time constraints are different. The dual format is different. So gauging whether or not something's easier or harder is one, very subjective, dependent upon learning styles, and really impossible to measure. So the answer to the question, would it be easier, is I don't know. Here, hang on, I'm getting a couple more questions in here. Okay. Let's see, another question. Is the ACS final a standardized thing to progress in chemistry? Okay, so the question is the ACS final a standardized mechanism to progress in chemistry? And the answer is yes and no. One, it is standardized, so it's the same across all the country, but it's so the exam difficulty problem sets are all the same, but you don't need to pass the ACS final to receive a passing grade in the first semester in general chemistry. Many universities don't use the ACS final. I'd even say most of the colleges that I've taught at have not used the ACS final. So you don't need to worry about if the concern is, will I be missing something if I don't take the ACS final? The answer is no. You won't be missing anything. It's a very specific testing format, one that is not universally accepted across all colleges. And if you want to know what it feels like to take the ACS exam, take the practice homework book that you have, pick 70 questions, sit down and see if you can do it in 1 hour and 50 minutes. And that will give you, if you want to know what that experience feels like, that's what it would feel like. But you're not missing out if you miss taking the ACS final. One more question. Let's see. I'm sure this is tough for you if you're a little one. Someone's asking. I'm sure this is hard for me if my baby is at home. Yes, but fortunately, my wife is handling the baby for me. So that is super, super awesome of her. So I have one last thing. We've been streaming for about 2 hours here, so it's been fun hanging out afterwards for the party chat session. I do have to run, but I have a thing to ask of you. So I will be going back to the stream later, just to kind of see how things went, and leave any comments I will totally be going back through and reading them. Things to think about. What was good? What was good about this? What was good? What was bad? What was good? What was bad? What could be improved? I will totally go back, read these. This is a, let's see, improved. Improved. What was good? What was bad? What could be improved? This is totally an experiment. This is the first time I'm doing lecture purely digitally. I want to know how you experienced it. I'm sure other professors are using Zoom and not YouTube. What's been your experience going YouTube versus Zoom? Because I'm not particularly married to one thing over the other. This can be a flexible arrangement. I want to know what your thoughts are, what your experience is, because I know all of us faculty are trying our best to connect and reach you with this very, very strange, like pre-apocalyptic higher education thing that we're all doing. So hopefully my hope is that this can develop, that this has been an effective tool and possibly develop into a better one. But that'll only happen with your feedback. So anyways, let me know. Tell me what you're thinking, and we'll reconvene here on Wednesday. Stay safe and maybe enjoy a good zombie apocalypse movie in between now and then. I'll see y'all soon.